There is a widely held view that modern bridges are built to last, with an expected life of at least 100 years. But do bridges live up to this expectation? Before answering this question, let's look back in time. In the early 50s, post-tensioning systems for the pre-stressing of concrete were developed by specialists, such as VSL International. This technique involves the introduction of internal stress into a concrete element. This is achieved by the installation and stressing of tendons. The internal stresses will then counteract the tensile stresses caused by external loading, and therefore reduce deformation and cracking of the concrete. Within a short period, post-tensioning revolutionized the design and construction of concrete bridges. It allowed the use of concrete for ever longer spans and enabled the development of new construction methods, making construction simpler and faster.
It was a big shock when in 1985, more than 30 years after successful use of post-engineering, all around the world, the precast segmental concrete bridge Años Iguals in the UK collapsed. The bridge failed because its longitudinal post-engineering had corroded where they crossed segmental joints. A more recent example which shows the importance of the durability of post-engineering for concrete bridges is the collapse of part of the Polgevera or Morandi viaduct in Genoa in 2018. This was a very bad accident since it's resulted in 43 fatalities.
Corrosion is a natural process. It is the electrochemical reaction of a metal with an oxidant, such as oxygen or an acid. In simple words, it turns the metal into rust, until finally, it breaks. To understand how corrosion is a threat to the durability of a post-tension concrete structure, let's dive into the heart of post-tensioning tendons.
Of course, post-tensioning tendon needs to be protected against corrosion. When a steel is exposed to oxygen or moisture or acids, or in the air with a humidity rate above 60%, corrosion starts to build up on the steel surface, resulting in the loss of steel cross-section, up ultimately to failure of the strand if happens. Various different methods exist to protect steel from corrosion: galvanization, coating, or simply making use of stainless steel material works. Nevertheless, the most suitable strategy for corrosion protection of strand from a post-tensioning tendon remains passivation of the strand itself.
Strands of post-tensioning tendon can be protected against corrosion by encasing it after the completion of the stressing operation. The strands are embedded in a cementitious grout, which has a high alkalinity. This method has been used since the invention of post-tensioning in the 50s. For the case of internal pre-stressing, the strands are placed into a corrugated metal duct, which is located inside the concrete. For the case of external pre-stressing, the strands are placed into a smooth polymer duct, which is located outside of the pre-stressed concrete girder. Cementitious grout is injected into a duct after the strands are stressed. During the injection, the grout moves along the duct and fills the entire length, including the anchorages and their caps. Once hardened, the cementitious grout passivates the strands due to the high alkalinity. However, this passivation layer of the strands can be attacked and destroyed by the different internal or external causes. That's why corrosion may still occur. The protection of this passivation layer is crucial for the durability of a post-tensioning tendon.
The strands of the tendon are surrounded by a protective barrier known as the passivation layer, designed to resist attack from two external sources. Firstly, the presence of CO2 in the atmosphere can carbonate concrete little by little, until eventually reaching and destroying the strand's protective layer. The second cause involves chloride ions, which come from salt spray in marine environments or the de-icing salts used in winter. Once they become highly concentrated at the strand's surface, they start to destroy the passivation layer and cause pitting corrosion on the steel strand. Obviously, destruction of the strand's protection is accelerated if the concrete is cracked. The protective layer's integrity can be compromised by two other factors arising inside the duct. The first happens if the strand's surface isn't fully protected because the duct wasn't completely filled during grouting. The presence of water and oxygen inside the duct can then result in electrochemical corrosion of the strands. The second occurs if the grout separates during injection, splitting into two parts: stable grout at the bottom of the tendon and unstable grout, also called soft grout, at the tendon's high points. This phenomenon is due to inadequate formulation of the grout and/or poor grouting procedures. The interface between the stable and the unstable grout acts as an electric cell, a battery in other words, which causes the flow of an electric current and leads to a very aggressive localized corrosion of the strands.
International Professional Association FIB introduced in 2005 the tendon protection strategy, which is applied in combination with the design strategy of a structure to define the adequate corrosion protection of a post-tensioning tendon over its life cycle. FIB introduced 3 protection levels, PL1, 2 and 3. The required protection level depends mainly on 2 things: the environmental aggressiveness to which the structure is exposed to, and the protection layer which the structure can provide around the tendon.
A post-tensioning tendon is rated PL1 when it has a corrugated steel duct. This duct is embedded in concrete, and once stressed, it is injected with a corrosion-inhibiting filling material. This solution provides durable corrosion protection for the strands. Leak tightness during injection is provided by the concrete surrounding the duct and by temporary grout caps. PL2 confines the tendon's filling material by use of an encapsulation that is leak-tight even without any contribution from the surrounding concrete. It is typically a corrugated or smooth plastic duct fitted along the full length of the tendon. The anchorages are kept leak-tight by permanent caps. PL3 provides the same protection as PL2, but also enables monitoring of the leak tightness of the tendon's encapsulation. This is achieved by measuring electrical resistance, both during assembly and throughout the service life of the tendon. Regular measurements allow early detection of critical sections where the encapsulation has been damaged. As a result, subsequent repairs can be carried out with surgical precision.
Corroded PT tendon can very quickly trigger the need to at least partially close a bridge to traffic. It can lead to major congestion, long detours, and at the end, of course, any affected PT tendon will have to be repaired, replaced, or substituted with new PT. So that comes as a major cost to the owners and operators, but also to individual road users and at the end to society. We do have today a lot of very sophisticated solutions to inspect, monitor, and repair post-tensioning tendons if they're affected by corrosion. So if we look a little bit at value for money, if we take a PL1 tendon, so basic post-tensioning tendon, as the base reference, you will only have to add about 10% additional cost of the installed system to upgrade this to an encapsulated PL2 tendon, and another 10% to get to a PL3 monitorable tendon. So that's only a small percentage of the overall construction cost of any bridge, but it's even a smaller fraction of the cost that you might have if you have to do later a major repair intervention.
The mitigation strategy against the internal attack scenario is to completely fill duct and anchorage with solid stable grout. In order to achieve that, you require quality grout mixes and you need to apply state-of-the-art grouting procedures.
VSL has summarized the most important aspects of state-of-the-art grouting procedures into 8 essential points. First, grouting must be executed and supervised by trained and certified staff, and an appropriate type of grout mixer has to be selected. A grout mix design can only be used on-site once it has been tested during the selected type of grout mixer. The inclined tube test is carried out with strands to confirm whether the grout mix bleed doesn't exceed specified quantities. The encapsulation has to be leak tight in order to completely fill a tendon without the formation of voids during injection. This must be checked by an air pressure test before grouting starts. During grout production and throughout the grout injection process, the grout mix has to pass a series of tests. Daily wick-induced tests, fluidity tests on samples taken from inlets and outlets, and density measurements taken at the outlets of each tendon. Passing all these tests ensures that the tendon is fully filled with grout of the right standard. Vacuum-assisted grouting should always be used for all types of tendons, in particular those with intermediate high points. Elimination of all air pockets ensures complete filling of the ducts. Full injection is guaranteed when a certain quantity of surplus grout exits from the duct ports. This surplus is collected and must be disposed of, without harm to the environment. And finally, the 8th measure is that detailed inspection is required 12 hours after completion of the grouting process. This guarantees that all anchorage caps and tendon ports are properly filled with grout that complies with the requirements.
Today, it's possible to verify the quality of the grout injected in the tendon at specific location by use of a void corrosion sensor, for example, VSL VC sensor. These sensors must be installed at critical location on the tendon, for example, behind the anchor head or at high points. And the quality of the grout is assessed by measurement of the changes of the ictal potential at these sensors. Electrical measurements are done during construction and during service life of the structure. The goal is to ensure the durability of the post-tensioning tendon and ultimately the safety of the structure.
In other words, it's now possible to get rid of the black box situation. After the complete installation of a cable, you can verify not only the leak tightness of the tendon's encapsulation, but you are also able to measure whether the duct has been completely filled with stable grout. The fact that these two most important characteristic of an internal bonded tendon can be verified after the tendon has been embedded in concrete and grout does significantly increase the as-built quality of tendons.
The best strategy overall to minimize life cycle costs is still to select durable PT systems from the start, to make sure they're properly installed, to check their final installed quality and document it, and to properly maintain the structures.
The collapse of the Anisquas Bridge in 1985 led to action from across the industry. International professional associations such as FIB and specialists like VSL initiated R&D into the design of grout mixes and correct grouting procedures. For instance, the inclined tube and the wick-induced test proposed by VSL and FIB were adopted in the Eurocode in 2007. FIB had already in 2005 introduced the protection level concept, which is integrated into the ongoing revision of Eurocode EN 1992. Even in the 2020s, the durability of post-tension tendons remains a challenge. But it is achievable if state-of-the-art procedures and testing are made mandatory in the technical specifications and consistently implemented by trained and certified crews in conjunction with long-term regular maintenance.
This is expected to, among other factors, allow bridges to last for at least 100 years.
And often far longer.